question number 30. This is a 1-mark numerical answer type question from thermodynamics. It basically tests your understanding of entropy changes in different processes, specifically comparing free expansions with reversible isothermal expansion. The question relies on a fundamental property of ideal gases that often trips students up. So let's read the problem. We have 1 mole of an ideal monoatomic gas at temperature T, which undergoes free expansion. So the expansion is free to double its volume. The entropy change, that is delta S1. Then we have an identical amount of the same gas at temperature 2T, which undergoes isothermal expansion. Isothermal expansion to double its volume again. The entropy change in this case is delta S2. We need to find the integer value of the ratio delta S1 over delta S2. So to solve this, we recall the general formula for the entropy change of an ideal gas. So this equation works for any process connecting two equilibrium states. The most important concept to remember here is that entropy is a state function. So entropy is a state function. So this is the general formula for entropy and the change in entropy. So it doesn't matter how you get from state A to state B, whether it's free expansion or a controlled reversible process. If the initial and final states are the same, the entropy change is the same because it is a state function. So this is a key concept to keep in mind. Now let us look at the first case, which is the free expansion. So since no heat enters and no work is done against a vacuum, the internal energy change delta U is 0 because dq and dw both are 0. So the internal energy change is also 0. For an ideal gas, internal energy depends only on temperature. Okay, so if internal energy U doesn't change, that means T also doesn't change. So since internal energy and temperature are dependent, since du is 0, we have delta T as well 0. So that means our T final is equal to T initial. Okay, so effectively the gas moves from volume V to 2V at the same temperature T. So using our master formula, that is the temperature term is 0 because the logarithm of 1 is 0, since logarithm of 1, both Tf and Ti are same, so we have first term as 0. Also the volume term, which is nR ln 2V over V, which is equal to R ln 2 now. Alright, then we can move to case number 2, which is the isothermal expansion at temperature 2T. So by definition, isothermal means the temperature is constant. So since the process is isothermal, the temperature is constant. So again, the first term in our entropy formula vanishes. So again, this term vanishes as we saw in the last slide. Now the volume change is identical, V going to 2V, twice the initial volume. So the entropy change is simply nR ln Vf over Vi, which is nothing but R ln twice V over V, which is, as we saw in the last slide, R ln 2. So notice something interesting here. The temperature 2T cancels out. It doesn't matter if the expansion happens at T or 2 times T or at 100T. So the change in entropy for an ideal gas doubling its volume isothermally is always R ln 2. Now let's conclude. Finally, we take the ratio, that is delta S1 over delta S2, which is R ln 2 over R ln 2, as we saw for both cases. So we get nothing but 1. So the answer is unity. So let us look at a key takeaway from this particular problem. So here is a key takeaway, and it is always a common trap. So you might think, wait a minute, free expansion is adiabatic. That means dq is 0. Shouldn't entropy change be 0? No. The integral dq over t only equals entropy change for reversible processes. Free expansion is highly irreversible. So this is for free expansion only, but as we saw that the free expansion is highly irreversible. So to calculate delta S, you must imagine a reversible path connecting the same states, which is exactly what case 2 was. That's why the answers are identical. So check out the thermodynamics lectures by Professor Dipankar Chakraborty. These are great sources. That's it for question number 30. See you in the next one.